Okay, so this one is gonna be a quick one because I want to talk about something. Well, it's something that I learned, right? So on this one is very short because what I learned is I'm learning it just now and it's not long, which is something that I have passion for, which is chemistry, but that happens in engines. And engines is not just like electric engines or like piston engines. Chemistry on engines has always been like a fascinating subject to me, and it's huge. It's like turbines, ion engines, rocket engines, piston engines, diesel engines. There's many different types of engines, like small, big, gigantic, and well, what I like, one of the things that I learned recently that I like a lot is I was always fascinated and I learned about how fuel interacts with the air so that you can improve efficiency. So let me detail a little bit more what do I mean. On piston engines and also on gas turbines, there is a very common knowledge about fuel richness, fuel mixture on the fuel mixture, like rich mixture or lean mixture. And it is very relevant on both of them. I am gonna focus right now more on the piston engine side because it is very related. I would have to explain why it's different on a turbine than on a piston engine, but the chemistry in reality is the same. And the thing that I learned about the chemistry is this. So let's start with this. Emissions are a big thing. The world has been moving to make internal combustion engines less harmful to the environment, and specifically to reduce pollutants that affect humans and pollutants that heavily affect the atmosphere. So CO2 is one of the lesser affecting ones. Methanes and ethanes affect quite a bit. HFCs affect quite a bit. Some nitrous oxides affect a bit too. And those are more like they affect humans a lot too. So we we do a lot to reduce those emissions. Now, one common thing that you can find and that you can learn about is that a rich mixture is gonna be is gonna have less emissions. And this is what I learned. So now I'm gonna detail what I learned. Now, the interesting thing is this. You don't really want a rich mixture because rich, by definition, you have excess fuel. And excess fuel is bad for efficiency. So, why are the reasons why engines today have rich mixtures? Well, first of all is emissions. They reduce emissions. Second is that they reduce exhaust temperature, which means the combustion temperature is lower. This happens, the chemistry of why this happens is fascinating. So let's tie this together for now. The reason why there is less emissions on a richer mixture is because of this. Fuel has a bigger molar mass than air. So air is composed of nitrogen, oxygen, and some smaller amounts of other elements. If you look at fuel though, fuel is mostly composed of molecules that are hydrocarbons. And hydrocarbons, depending on the bonding, they can be very clumped up together. And they're usually, for starters, on a liquid too. So maybe then a molar mass is wrong. No, but it is molar. It's just I don't know how to use the correct words, but okay. So the terminology is this: most hydrocarbon fuels will have a higher specific heat ratio than just compressed air. And what does that mean? That means that for every particle and I think molar mass is correct to say, for every molar mass of fuel that you have compared to air, heating up fuel is gonna take up more heat than air is gonna absorb. So if you have a Rix mixture, that means you have the same amount of combustion because the combustion is gonna be stoichiometric, but the excess fuel is gonna mean that the fuel itself is gonna absorb more heat. So you have a lower combustion temperature, and lower combustion temperature makes less harmful emissions. Let's be clear on that one, because the emissions in reality is the same, since it's a stoichiometric thing. That's kind of like the other thing that I learned. In reality, there's many small reactions that happen super fast, and it's in the order of microseconds and picoseconds inside of a flame. But that's kind of like a study of that I'm gonna do later on. I'm gonna talk about that later on. I'm tired right now. But then going back to what I was talking about, then I explained why a rich mixture has lower emissions and has a lower temperature. Now, based on that, let's go now to a lean mixture. A lean mixture means that there is more molecules of air than there is fuel in order to be stoichiometric. That means that in theory, all of the fuel is going to combust. Now, all of the fuel combusting is going to make up a certain amount of heat, but the heat is better absorbed by fuel than by air. So that means that a lean mixture is going to get hotter because there is more air than fuel. And fuel is the one that is much, much, much better at absorbing heat than the air. So this took me a long time to learn. I didn't know. I didn't understand why a lean mixture would burn hotter than a rich one. But now I know. And the chemistry is fascinating. I had to learn about a lot of stuff in order to understand this. And it is quite cool. But no, like in all seriousness, it's I was fascinated when I learned this. Like when I finally understood why lean mixtures burn hotter and cause more emissions, it was like fascinating to me. And one of the cool things that I want to end this video on is that, some people, I guess, not everyone, but they're kind of like, internal combustion engines, such an old technology, like electric engines are just so much better, and electric is the future, and blah blah, and hydrogen and all of this. But sometimes I get caught up on it too. But the reality is this: research and technology innovations for internal combustion engines advanced too. You know, if you want to talk about that, I'll briefly touch on turbine engines. The evolution and the emission reduction and the efficiency increase of turbine engines has been astronomical. If you compare a plane design on the 1950s to a plane design on the 2000s, like they're like magnitudes more efficient. It's insane. And not just because of the plane design, but like the engine efficiency increased too. And hydrocarbon fuel does have a future just because electric is too heavy and not dense enough, and hydrogen is just a completely unproven technology. So I am confident that within my life cycle, I'm not gonna see hydrocarbon fuels go extinct, because the improvements are very clear. Like, you can clearly tell that the efficiency can be increased and that the engineering can be better on an internal combustion engine. It's just, it was a little bit slower than the innovation on battery technology and battery manufacturing, let's put it that way. So yeah, I mean, it's just that I want to be kind of like, let people know to be a little bit less pessimistic on that. You know, the research and the industry and the economy of fuel and hydrocarbons and oil and internal combustion engines is not a is not going to go extinct anytime soon. It is an ongoing research and an ongoing improving technology that humanity has created. And yes, on certain applications like cars and like small airplanes and small drones and robotics, batteries plus electric motors is just so much better. But that's not the entire world. Like, for example, I'm going to give you an example again, a different one, where probably we're not going to see hydrocarbons go away. Marine diesel engines are insane. Marine diesel engines, they can become the size of like entire buildings. Like, if you grab like a New York small apartment building and flip it on its side, that's more or less the engine room on like a shipping container. They're massive things. And also, the chemistry and the engineering that goes into them is like enormous. Like, these things are super, super efficient. And the chemistry and the research that has been going into this, it's ongoing, and it's a huge industry. So it's something that I like, and I wanted to kind of put it out there, the stuff that I learned and the very interesting stuff. And that's it. That's pretty much it for today.